In this section, we'll talk about UML sequence diagrams. The sequence diagram is a kind of interaction diagram because it describes how groups of objects collaborate in some kind of behavior. In particular, the sequence diagram shows how objects call the methods of other objects during a particular execution of a program. This is an example of a sequence diagram. Notice that the rectangles across the top are labeled with object names, not class names. An order rather than just order. An order line rather than just order line. A product and a customer. These represent particular instances of a class rather than the classes themselves. A good way to think about this diagram is like a story that's being told about what happens during the execution of a particular method. In this case, the method we're observing is calculate price. During the execution of this program, an order is being processed. We begin our story when the method calculate price is called. The method we're observing is known as the found message. The method can be found in the order class. We know this because the arrow for calculate price in the diagram points to the order object. A long rectangle underneath the order object represents the lifespan of the calculate price method. Working your way from top to bottom, you can see that the first method call that calculate price calls is the method getQuantity in the order line object. That means that the order line class implements the getQuantity method. When you have a descriptive method name like getQuantity, you can assume that it does what it says. In this case, it returns the quantity to the calculate price method. Then, calculate price calls getProduct from the order line object, and the product is returned. Here, the return is explicit, but this is really just for educational purposes. With a method called getProduct, you can probably just infer what's returned. One thing to notice here is that in the class diagram we looked at, the order class held a list of order lines. So that's how it has access to the order line object here. However, it needs to call a method that belongs to the product. So it has to get the product from the order line object before it can call the method. Now that calculate price has access to the product, it gets the pricing details. Once it has access to the pricing details, it uses them and the quantity to calculate the base price for the order line. But why is the arrow for calculate base price pointing back to the lifeline of the order object? I won't ask you to pause the video here, but if I give you 10 seconds, can you tell me what it means that the arrow for calculate base price is pointing back to the lifeline of the same object it's being called from? 10 seconds starting now. Okay, the reason the arrow is pointing to the order object is because that's where the method is. So the order class will have a method called calculate price, but it'll also have a method called calculate base price. So most likely the method calculate base price is a helper method that has private access so that only methods within the order object can call it. Finally, calculate price calls another helper method, calculate discounts, which in turn calls a method in the customer object to get the discount information. Once the discount information is obtained, calculate price can finally calculate the full price for the order line, and the method terminates. Here's another sequence diagram. This one shows a method with a parameter. Also, something interesting is happening here with the call getDiscountedValue. The caller, an order, is passing itself as a parameter. and then the customer is calling back to the order object to obtain the base value. This is known as a callback, and some programmers find this convenient to use. Personally, I try to avoid code with callbacks because they make it more complicated to reason about what's happening to the code. Also, they lead to more coupling, which is something developers should really try to avoid. In this case, if the customer object is going to use the order object to get a base value, I think it would be preferable to pass the base value as a parameter to get discounted value in the first place, rather than pass the entire order object. Okay, let's get back to the sequence diagram. Here's what's interesting. This is a sequence diagram for the found message calculate price. But the other sequence diagram was also for the found message calculate price. Fowler refers to the other sequence diagram as being for centralized control, and he refers to this one as being for distributed control. So let me ask you this question. What do these two different sequence diagrams, the centralized and the distributed one, represent? And I'll give you a couple choices here. A, do they represent two different ways of visualizing the same method, calculate price, in the order class? B, do they represent two different executions of the same method? Or C, do they represent two completely different ways of implementing the calculate price method? Please pause the video and try to figure out which answer is correct. Ready? And the answer is C. These are two completely different ways of implementing the calculate price method. In the centralized implementation, the calculate price method is doing all the work. It's grabbing information from other objects and then doing the calculations on its own. In the distributed implementation, calculate price is delegating tasks to other objects, and it even goes so far as to give all of its information to the customer object so that the customer object can calculate the final price. Which implementation is better? Well, it depends on what kind of system you want. But let's see what Fowler has to say. Interesting. Object bigots like Fowler strongly prefer distributed control because it localizes the effects of change. The key principle of object-oriented programming is that data and the operations that manipulate that data are encapsulated into the same component, a class. And this is a key way of localizing the effects of change. Now, I am mostly in agreement with Fowler, but as I stated in the previous slide, I don't see the need for that callback. Fix it up the way I described, and I will be completely on board with Fowler on this one. Remember we said that sequence diagrams showed a particular execution of your code. Well, that's mostly true, but a lot of smart folks have tried to generalize sequence diagrams so that they could show arbitrary executions of code. There are ways to represent loops, conditionals, and optional behaviors, as in the diagram on the right. However, I tend to agree with Fowler here. This is really not what sequence diagrams are good at. The activity diagram, on the other hand, excels at showing alternative behaviors. So you're much better off using that diagram when you want to illustrate control flow through your program.